Hi, yeah, thanks. My name is Ferdinand Schenck, and I'm going to talk to you today about using foundation models for very high resolution bitemporal change detection, and I'll explain a little bit what this means. I work for a company called LiveEO. We're based here in Berlin, established in about 2018. We have offices in Germany, the UK, the US, and Latvia, but our main office is right here in Berlin at Schleswig. We have about over 150 employees at this point. I think we hit 160 recently. And yeah, we serve customers in about 60 different countries. So as the name suggests, LiveEO, live Earth observation, we deliver enterprise-ready insights from satellite data at scale. So we use a lot of satellite imagery to deliver products to our customers. So LiveEO has three main products at the moment. Treeline, which is satellite-based vegetation management for line infrastructure. This is power lines, railway lines, and yeah, that kind of thing. We have Surface Scout, which is automated detection of third-party interference along pipelines. These are usually gas or oil pipelines. And then we have a product called TradeAware, which is deforestation detection and compliance management, mostly in the context of the EUDR, which is the European Union Deforestation Regulation, which is coming into effect at the end of this year. So today's talk is going to be focused on Surface Scout, which is automated detection of third-party interference along pipelines. What does this mean? Oh, just a quick note, if you were here earlier this week, my colleague Vin gave a talk about streaming satellite data for analysis-ready outputs, where he talked about how we actually go about ingesting and storing and distributing satellite imagery that downstream analyses can use, and I'm now going to talk about one of these downstream analyses that are enabled by the work of Vin and the others in the company. So the business problem that we're trying to solve for our customers is that gas and oil pipelines are vulnerable to human or natural activities such as construction, farming activities, or erosion. These pipelines are usually buried about 1 meter to 1.5 meters underground, which means any kind of digging or driving of poles or anything can actually interfere with these pipelines. If you look at this report from the European Gas Incidence Group, you can see that external interference, which means people digging holes or doing anything like this, is one of the main drivers in holes that are created in gas pipelines. And the pipeline operators are required to perform regular inspections, usually on the order of between every 2 weeks to every 2 months, depending slightly on where in the world they are and what kind of gas pipelines they operate. But yeah, they have to do regular inspections just to make sure that nothing bad is happening along their pipelines. And if you don't think anything like this actually happens, then yeah, I invite you to have a quick look at this GIF here. So the guy's fine. He walked away from this. I'll move on from this one now. He's fine. He walked away from it. He had to pay a big fine because he destroyed some infrastructure because he didn't get the necessary permits before starting to dig poles in there. But yeah, bad things can happen. I also have to point out that that was more like low pressure distribution pipelines, which are just from house to house. The kind of pipelines we usually work with are the more high pressure pipelines, which transmit gas between cities and so forth. And those things carry a lot more gas that are under a lot higher pressure, and when things go wrong there, they tend to be a little bit more explosive than what you just saw there. Okay, what tools do we have to solve this problem with? So we're a satellite-based company, and for a lot of reasons, satellite imagery is really nice. It's very scalable. Satellite imagery is very homogeneous across the globe. But satellite imagery isn't just satellite imagery. There are a lot of different satellites up there with a lot of different characteristics. One of the main characteristics is ground sampling distance, and you'll hear this term a lot. And this is effectively the resolution of the satellite. Ground sampling distance means just if it's what's the size of the pixel on Earth. So if a satellite has a ground sampling distance of about 60 meters, this means that every pixel is about 60 by 60 meters. Now this is good if you're mapping things like mountains or oceans or really large scale phenomena. And it gets all the way down to about 30 centimeters. There might even be a company launching 10 centimeter satellites, but the highest you can commercially get is about 30 centimeters, in which case every pixel is about 30 centimeters by 30 centimeters, in which case you can really tell things like vehicles and cars and relatively small buildings and things like that. So depending on what your use case is, it'll depend a lot on what kind of resolution the satellite imagery is at that you're going to be using. There's also the effect of cost. We're a commercial Earth observation company, so cost is quite important to us because we need to be able to deliver our products at a certain cost. And generally, for the lower resolution stuff, you can quite often get this for free. Like you can get up to 10-meter ground sampling distance imagery from the Sentinel-2 mission from the European Space Agency for free. But anything above that, you have to start paying. And in general, the higher resolution you are, the more you start paying. So if you just want to kind of see this visually, for example, like a 10-meter ground sampling distance image, a like an oil tank like this might only be about like 20 pixels in total, not 4 pixels by 5 pixels or so. Versus if you're looking at this at like 30-centimeter imagery, you might have hundreds of pixels for an oil tank, which means you can see a lot more detail. And yeah, this is just like one of the factors to take into consideration when you think about like the size of the phenomena that you are trying to look at. In our case, we're trying to look at things that are going to be affecting gas pipelines. This generally means things like construction vehicles or ditches that people are digging. So these are going to be things that are on the order of like single-digit meters, which means that we need satellite imagery of the ground sampling distance of usually below a meter to really realistically see these kind of things. So what do we need? We need a high revisit rate, like I said. We need to deliver this to our customers on every 2 weeks to 2 months. We need a sub-meter ground sampling distance because we need to be able to see phenomena on the order of like a meter or two. And we also need the data to be at a reasonable cost. This is important, again, because above a certain price point, this just doesn't make financial sense to our customers, and they might find another solution, like sending a helicopter or something else like that out. So what we've settled on is the SkySat constellation by Planet. There are currently about 15 of these satellites up there. There used to be more, but they deorbited a few of them in the past. And some of the characteristics are that with 15 satellites, you can usually get a daily revisit rate of about like 7 times per day. It has about a 75-centimeter ground sampling distance. It changes a little bit between satellite to satellite, which they upsample to 50 centimeters, but let's not get into that. And it costs like on the order of like hundreds of euros per capture, just to give you an idea of like what we pay for this. I don't know what the exact number is over there. But the technical problem, we've essentially phrased it as a bitemporal change detection problem, which means that you have one time step, you have a second time step, and you have to say like what relevant has changed between these two images. In this image, you can see here, you can see this black line, which is where the pipeline of our customer goes, and the red is just the bounding box that shows detected change. In this case, someone has been digging a hole on top of this gas pipeline. In this case, this might well be the gas pipeline operator themselves doing some maintenance work. We're never really sure, but these are the kind of things we need to flag to our customers. Another example is, for example, here, where someone has created a road, or between the first time step and the second time step, and this is a fairly obvious change. You can easily see that the road isn't there in the previous one, the road is there in the next one, or at least the surface of the road has changed. But you might also notice that like the two images look a little bit different. The one is quite a lot darker, the greens are a lot more saturated, there are even clouds in the corner of this one image, if you're wondering what that fluffy white stuff is. So it turns out that the problem isn't really like detecting just visual changes. The problem is actually distinguishing between like what we call semantic and non-semantic changes, i.e. like changes that are relevant to our problem and changes that are not relevant to our problem. And that's really where things get difficult. So this is an example taken from a paper called SatGS, and here you can see some examples of like non-semantic changes. This is, for example, like seasonal variation. The fact that trees lose their leaves or the leaves change color, completely irrelevant to us. Also things like shadows or cars that are just moving, also completely irrelevant. These are irrelevant changes, and if we tell our customer, hey, look, there's a shadow here, they'll tell us to, go walk away and go do something else because it's not useful information to them. But, these are visual changes, and we need to be able to train a model that understands that these are not relevant changes. So how do we get our training data? The natural way to do this would be to deliver our product for our customers, just do it manually, just label on our customers' data, and then train a model doing that. The problem is, especially at the kind of timelines that we're working with, quite often these pipelines run in very rural areas in the desert, pretty far away from people. And if we're doing a frequency of about 2 weeks, in 2 weeks, not much usually changes. So if you're doing that, we're paying hundreds of euros per image, and we're getting on average about like 1 change per image. This is just like a very inefficient way of collecting label data. And this just means that you have to collect loads and loads and loads of data before you have enough to really start training a model. So can we do better? So how we got around this is that we looked into the SkySat archive. We buy quite a lot of data from SkySat, from Planet, and they allowed us to look at the SkySat archive. And so what this basically means is that this is a bunch of old images that were taken for other projects that you can now go and buy for a lower price from them. So usually we task imagery, which means we say, hey, please go take an image here now, and that costs quite a bit of money, but once that's been taken, someone else can go and buy that image for a little bit cheaper. So Planet can squeeze more money out of the same imagery that they've taken. So what we've done is we are searching the archive for image pairs that are at least 365 days apart. It just means the more time there is between two images, the more chance there is that something has changed. We're looking for images near human activity because where there are people, there are changes. In the desert, even over a year, nothing might really change, but close to human infrastructure like airports or buildings or things like humans change things. And we want also imagery across different geographic regions. We serve customers all around the globe, and whether we have served customers in the desert regions, and we serve customers in temperate regions and tropical regions, and we need to be able to support all of these customers. So we need our models to understand all of these different geographies. So once we do that, when we search the archive with these criteria, we are left with a data set that looks visualized something like this. This is a bit of a heat map. So you can just see that where the color is more yellow, there's more data. But you can see there is quite a lot of data available to us. Most of it's in the US, China, like Europe, but there's also a little bit in Australia, Africa, and other places. So our labeling strategy. What we then do is we take our two images, our before image, our after image, and we have our labeling studio or labelers. They then go and label any changes for us that are important to our clients. Like in this case, you can see someone seems to be grading a road or clearing some area. And this is usually a sign that some construction is going to start. And this is the kind of things that our customers do want to know about before they become a problem. The resulting data set that we got by doing this, and this is of May of this year, which is when we wrote the abstract for this conference. We had about 6 labeled scenes, of which we used 5 for training and 1 for testing. This was about 6,000 changed polygons and about like 1,600 labeled 500 by 500 row patches. By now we have a lot more data, but back when we were talking about this, we did this test, this was kind of what was available to us. So if you know anything about like deep learning, you'll know that 1,600 images is not that much. Usually you need tens of thousands or preferably hundreds, if not millions of images to really train your model to properly understand your data. So we don't really have enough data to train much of a big model. This is enough to train a relatively small model, but a relatively small model might not really understand all the complexities that it needs to really solve this problem, i.e. it might not understand the difference between shadows and other changes and all that kind of things. So our problem is that we have limited labels because getting labels is expensive. It's really time consuming for people to label these scenes. It's hard to acquire labels in lots of different contexts. And we need our models to generalize across a large variation in biomes, solar angles, view angles. You can imagine if we're only training a model, like I said here, on 5 images, this means this model has only seen 5 different solar angles, 5 different view angles, and probably, I think the data set was only of 1 biome. It has seen pretty much no seasonal variation and hasn't really seen much different seasonal land use patterns. So we really need a model that can understand all of this and really understand this kind of data. So taking a step back, when you train a neural network, you usually give your neural network some data and you give it some labels and you say, hey, given this data, please predict these labels for me. And this is how this solves this task. And effectively what you're doing, and the way I like to think about it, is you're effectively training a model to solve your task and to understand your data at the same time in the kind of most naive fashion. So what if we could separate these steps? What if we could make our model first understand the data and then train it to solve a task? And this is effectively where foundation models come in. What you do with foundation models generally is you train a big model on a large corpus of unlabeled data, and basically in this step, you teach your model how to understand the data. And what you then do is you then take your model and you adapt it or fine-tune it downstream for a lot of different possible tasks, and then you fine-tune your model to understand your specific task. And yeah, the reason they're called foundation models is because they're effectively, you can think of them as the foundation on which you can build a lot of different possible models. And if, pushing the analogy a little bit further, is that the stronger and better your foundation is, the bigger and better the house you can build on top. The bigger the better and the more capable the model you can build on top of these foundations really is. So this is just a side note, but one of the normal ways that this is quite often done in the vision domain at the moment is masked autoencoder pre-training. This is from a paper called Masked Autoencoders or Scalable Vision Learners, which is a very influential paper in the field. And this is effectively a way of teaching your model to understand your data without needing any labels. The cool thing is here you can just give your model a lot of unlabeled data and teach it to understand the data by giving it some pretext task. In this case, the pretext task is reconstructing the image. So what you do is you take your image, you mask out a certain fraction of your image, either 50% or 70% or something, and you tell your model, like, hey, here is 70% of, or 30% of my image. Please reconstruct the other 70% of the image, go. And because you already have the label, that's just the full image, and you can give it the input quite easily, so you can just synthetically create this task. And this turns out to be a pretty good way to train a model. This means because data is cheap, like as my colleague Vin earlier said, we have terabytes and terabytes of satellite data, it's just the labels that are expensive. And so this is a way of using this like loads and loads of unlabeled data to make your model understand the data. And then you can then further fine-tune your model to actually understand your task once it's already understood your data. So, geospatial foundation models are a very hot topic at the moment. If you're in the geospatial field, you might already know this, but it feels like every week I turn around and there is a newer, better geospatial foundation model. So yeah, I'm not going to go through these in depth. If you're interested, just go look them up. Prithvi was at one point the hot thing, and then there's a lot of other ones which have come out by now. Even the big players have jumped in recently. There was a recent release by Google DeepMind, which was called Alpha Foundation, which is a foundation model trained on a lot of geospatial data. They haven't actually released the model, they just released embeddings based on the model, but still, they have a model internally somewhere. And yeah, it's attracted a lot of attention out of a lot of corners recently. So, we wanted to answer the question about foundation models. We wanted to ask, we had a few questions we wanted to answer. It's like, do we need foundation models, or will smaller models suffice? Do we need geospatial foundation models, or will general purpose foundation models, i.e. just ones trained on natural images, work? Does the ground sampling distance of the training data matter, i.e. in geospatial data, does it care if we use low resolution or high resolution imagery? How big of a model is big enough to solve our specific task? And do we need to train our own foundation model, or can we just use one off the shelf? Of course, if we don't have to go through all the hassle of training our own foundation model, that would be great. It saves us a lot of time and effort and money, and that's what we would prefer. But if we do need to train our own, we will. So we set up a little test here. We used a little baseline model, which is ChangeFormer, which is just a small vision transformer coming in at about 14 million parameters, which in this day and age is tiny. And then we have a couple of 100 million parameter models that we used. The reason we chose this is because there were quite a few geospatial foundation models, or foundation models in general, at this parameter count. And we wanted to do like a really apples to apples comparison. We didn't want to use like a large model and compare it to a small model. We really wanted to have like everything be as close together as possible. So the models that we tried out for this is Dino V2 with the original weights trained on natural images by Meta, Facebook, and then someone else trained a version of Dino V2, the guy's called Kun Cha, on remote sensing weights. So basically the same model architecture, just trained on remote sensing imagery. We used Clay V1, which is the Clay Foundation model, Clay model trained by the Clay Foundation. This was trained on high and low resolution remote sensing imagery. They now have V2 out, I believe. Prithvi V1, which was trained by NASA and IBM on a lot of lower resolution, so higher ground sampling distance geospatial imagery, which was trained by NASA and IBM. They also have a version 2 out in the meantime. And then just a vision transformer with multitask pre-training trained by Millilab at Wuhan University in China. And then basically, I'll explain what multitask pre-training is in a second, and then basically just the bigger brother of that, because we want to also test like, hey, does size matter? And then we trained the 300 million parameter version of this last model. Where's my next slide? Yeah, so you can also think about it just in terms of like, you can split these models up into what data they were trained on. ChangeFormer and Dino v2 with the original weights were trained on natural images. Prithvi v1 was only trained on low resolution geospatial data. Dino v2 was trained on a mix of lower and higher resolution geospatial data, and the vision transformers I talked about were trained on all three in some way. Just a quick note on multitask pre-training. Multitask pre-training, like previously we said, we effectively now have a two-step process where we first train our model on the data in a self-supervised fashion, and then train it on our task to solve our task. Here they effectively added a third step where they did the self-supervised pre-training. Then they trained the model on a bunch of common remote sensing tasks in a supervised fashion, just with a lot of like open data sets that already exist, like for specific tasks. So this is object detection, instance segmentation, and semantic segmentation. And then you finally fine-tune it. So you turn this into a three-step process. You can kind of think about this as you've already taught your model how to solve a bunch of pretty common like remote sensing tasks before you then fine-tune it on your specific task. And yeah, without much further ado, what results did we see when they did this little test? We saw some slightly surprising ones in the fact that like Prithvi v1 did pretty poorly, even though it was trained on remote sensing images. These images are quite different from the images that we eventually ended up using. Basically, the ground sampling distance that they used was about 30 meters, and we used about 70 centimeters, so there's just a pretty big disconnect there. Plus, they used images trained on 7 spectral bands, and we only used 3 RGB bands. A randomly initialized vision transformer, i.e. vision transformer trained without any randomly initialized weights, did a little bit better than Prithvi, but still not very good. The original Dino v2 didn't do very well, but still a little bit better than initializing a vision transformer from scratch. Our baseline did quite a bit better than that already, and this just shows you what like a small model can do. Then Clay v1 did a little bit better than that, even though it was trained on remote sensing images. It didn't do much better than a small model, and this is where things really get interesting. This Dino v2 with remote sensing weights was actually trained on exactly the same model architecture as the previous Dino v2, except it was just trained on different data. And already here you can see there's starting to be a clear gap in performance. Then a vision transformer trained just with masked autoencoded pre-training does a little bit better. When you add RVSA, which I don't have time to get into, does slightly better. And then when you add the multitask pre-training, there's quite a big jump. And then our final test was like, hey, what if we make this final model just a little bit bigger? And as you can see, there's quite a jump in performance here. This is expected. In general, bigger models are more performant, given if everything else is equal. And this seems to be what we see in this case. So, we see that bigger models are better. If you would just want to have a little bit of a look of like what this looks like on our actual customer data, here are some examples. One pretty good example, which is like the image at the first time step, the image at the second time step. At the bottom left, yes, that's what was labeled by our annotators. And on the right, this is what's predicted by our model. As you can see, this is a pretty good match. The model does a pretty good job of detecting the changes. On the right, the model does less of a good job. You can see here the changes are a little bit subtle. Our images are a little bit blurred, and it's not doing very well at like very small changes yet. This has gotten better since then. This was kind of the state of things around May of this year. But yeah, there's still some work to be done. So our takeaways here. We've definitely seen that foundation models make a difference. Foundation models do quite a bit better than just training small models. Remote sensing images matter. We can see that the models trained on remote sensing images do quite a lot better than the models trained on natural images. The ground sampling distance seems to matter, i.e. the models that were trained on high resolution remote sensing images do better than the ones trained only on low resolution ones. Bigger is better, so bigger models are more performant. And multitask pre-training does seem to help a little bit in getting that last little bit of performance out there. We still need to clarify a few things, like, can we go even bigger? This starts to get a little bit expensive and stuff, but yeah, there are, like we use the base and large vision transformer. There's also huge versions of the vision transformer. And should we train the SkySat foundation model? Because that's the data source we're using. We don't know the answer to that. I don't know how to answer this without actually training a SkySat foundation model. But yeah, this is something we might go through in the future. Is what I would have said until last week. Oh no, sorry, 3 weeks ago. So 3 weeks ago, after I already written my presentation and done all the tests and everything, Meta released Dino v3, which, v3 bigger than v2, which they trained on 1.7 billion images, which is absolutely enormous. They also trained a version on it on a satellite imagery data set that contains 493 million images. This is just like, we have 1,600 labeled images. They trained this on 500 million images. It's an enormous model. And they actually, have an entire section in the paper on geospatial data. So it's very interesting to see that like the big players like Meta are also jumping into this geospatial world at the moment. There are some interesting things to note. It seems to be one of the best performing models on GeoBench, which is a suite of benchmark tests for geospatial foundation models. Although the very interesting thing to note here is actually the one trained on the natural images is mostly outperforming the one trained on the satellite imagery, which is very weird and slightly unexpected, but it's something that I want to unpack. Unfortunately, the paper came out just before I had to travel to the US for work, but this is what I'm going to be doing next week, like digging a little bit into these details. And yeah, thank you very much for coming to my talk. My name is Ferdinand Schenck. I did this work in association with two of my colleagues, Paul Weinmann and Martin Schicklar. And in case you want to work with us, we're currently hiring for 2 positions in tech. Yep, thanks. Also, if you're interested in references, you can go look up some of the references here.
That's a great presentation. So there are a few questions. The first one, how do you deal with bias during the training data, especially on changes that are too long apart from each other?
Yeah, no, that's an excellent question. So what this comes down to, and this is a very good point, or I'm interpreting this question like this, is the fact that the types of changes that we've chosen it so that our images are taken about at least a year apart. They're sometimes a year, sometimes 2 years apart, sometimes 3 years apart. The types of changes that you see over a year, 2 years, or 3 years is actually much different from the types of changes that happen in only like 2 weeks or 2 months or something like that. Because you can imagine in 2 years, people have built an entire house. In 2 weeks, they just start digging the foundation. The way we currently deal with that is that we actually have like a 3-step process where we take the foundation model, then we train it on this corpus of large labeled data, and then we kind of fine-tune it finally on the small amount of more like data that we collect naturally from our customers. So we do actually use the customer data that we use for deliveries. We just like do the fine-tuning on that so we can actually like take away that bias. But it's important bias, and it is something we do think about.
Yeah. The next question, you showed the F1 scores in one of your slides at 0.6
yes.
or even 0.5 actually. Would you consider it good enough?
That's a good question. So, I mean, just for context, like this is work that we did quite a while ago. Things are higher at the moment. This is the F1 score. I didn't really go into what that means or why that is, and it's the pixel-wise F1 score. It's really hard connecting metric to business value that much. We've also, in the meantime, started adding things like object-wise metrics and seeing like more like less like, oh, how many pixels did it get correctly and to more like see like how many objects did it detect correctly, because that's a little bit more in line with what our customers care about. Like our customers really don't care like, oh, it got every single pixel of this correct. Right now, it's already delivering value. Okay, the scores we're seeing at the moment, like for the models that we're using in production, are quite a bit better than what you see here. This was just the first little test that we did to decide which models to go for. Like we didn't keep on training every model every time. We chose one model and then went on with that. But yeah, at the moment, like it does the job pretty well. We still use a little bit of like manual QA. If we think the model isn't doing a good job, we'll have manual people check it. But we're using that information about where the model fails to like continuously improve our model as well.
The other question is on, was overfitting a problem training foundation models? Did you try out augmentation techniques to generalize better on data?
Yeah, no, definitely. We do a lot of augmentation because there's a lot that can happen. Like there are a lot of different things. For example, one of the big augmentations we actually do is, for example, like clouds and haze. We have a lot of things like cloud shadows and haze that sometimes go in there, and this results in like large visual changes, but no real semantic changes. For example, like cloud shadows, like sometimes you have half your image being shadowed, and then suddenly, like before we trained it with these augmentations, the model would just predict a big change under the cloud shadow because that's a big visual change, and then we started adding augmentations for cloud shadows and to make it robust. So it is something we think about a lot, in addition to the like normal things like rotations and like a little bit of like degradation of the data. You can see our data is often a little bit, if I can find an example, our data is often a little bit blurry, so we sometimes like add blur and stuff like that.
Do you have pipelines which are above the ground or always?
Good question.
But then the shadows come and...
They're mostly underground. They're above ground close to like terminals or things like that, but that's usually where people can see them. But usually by the time the pipeline's above ground, it's usually a problem. And usually the areas that are above ground, there are usually people around, so they don't really care that much about monitoring those ones. But I'm not a gas pipeline operator. I'm a machine learning engineer, so I don't know, like take that with a grain of salt.
Are there any other questions quickly? Yeah, just one.
So you mentioned you have some, let's say you're sourcing your image data from, for example, Planet, and I don't remember the name of the other one. So is it also the case that because they have so much of data, are they also looking into making these models and maybe even eventually providing APIs?
Yeah, like I actually wrote like an entire like blog post about that, like thinking that like maybe they will create these models. I know like especially Planet has a bit of a machine learning team, but they haven't made any of these models. They haven't like made any models available as far as I know. And it's actually kind of interesting. I was thinking like maybe that's what's going to happen. Maybe Planet or one of the other providers like Airbus or someone would actually create a model. But now, especially with like Dino V3 coming out from Meta, they seem to have partnered up with Maxar, one of the leading imagery, satellite imagery providers. And this data is completely from Maxar's very high resolution data set. So I would thought so, but now I think it's probably more likely going to be someone like Meta or Google or one of those players who'll probably do it in partnership with those companies.
So thanks a lot for the great presentation. Please thank Ferdinand again.